Let's take a look now at the concept of the cross product. One thing to note is that the cross product is only defined in 3 dimensions. We will not be looking at a cross product in the plane where it's not defined. So here we start with a definition. Again, these are 2 vectors in space. We do not define the cross product in the plane. So assuming you have 2 vectors in space, u is denoted by u1i plus u2j plus u3k, and v denoted v1i plus v2j plus v3k, or if you prefer the component form, u1, u2, u3, v1, v2, v3. Then, given those 2 vectors in space, the cross product is defined as follows. First of all, we have a notation. We have the familiar multiplication symbol. It's called the cross product because, well, we use a cross to denote multiplication, as opposed to a dot for the dot product. So, u cross v is given by u2 times v3 minus u3 times v2i minus u1 times v3 minus u3 times v1j plus u1 v2 minus u2 v1k. Notice that the cross product is a vector. It has the 3 components of a vector in space. The dot product of 2 vectors is a scalar. The cross product of 2 vectors is another vector. This definition might be a little difficult to remember. Fortunately, we have a nice mnemonic that allows us to remember this product without having to remember it exactly this way. Now, there's nothing wrong with remembering it this way, and if you have the memory space to remember that, then that's perfectly fine. But if you're like me and you just have no hope of remembering that order, in that case, we go ahead and have a slightly different way of remembering this. So that doesn't change the definition. This is the definition. However, a way to help remember. Let's say we have the vector u, which is given by, and again we have our 3 components, u1i plus u2j plus u3k. And let's say we have the vector v, which is given by v1i plus v2j plus v3k. Let's compute the cross product of these 2. One way of doing that is the following. We're going to start by writing the unit vectors, I, j, and k. We're going to write those, I, j, and k. Notice I'm leaving a little space there. There's a reason for that. And then I'm going to take this and I'm just going to write it again. I, j, k. This may not seem to have any rhyme or reason, but we're not done yet. Next thing we're going to do is we're going to take the components of the first vector. We're going to take the components of u, and we're going to write them down right underneath here. Now you notice there's only 3 of these. Okay, but just like this, we'll repeat it. We'll say it twice. So this will be u1, u2, u3. And then we'll just say it again, u1, u2, u3. Okay? And then we'll do the same thing with v. That'll be v1, v2, and v3. And we'll do it again. Just like that. Okay, so now what? Well, now we're going to multiply. Starting from here, we're going to take diagonals, going down and to the right. So here we're going to multiply these 3 items together. So this is u2 v3 times I. So u2 v3 I. And then we'll do it again. That's going to be what? u3 v1j, u3 v1j. And then you're going to take these and you're going to multiply those as well. That's u1 v2k, u1 v2k. Add all those together. Now you're going to go backwards. You're going to start from back here. And now instead of taking a diagonal from upper left to lower right, we'll go from upper right back to lower left. So here that's V1 U2K. I'm going to put that one right underneath here because that one's also K. So that'll be what? V1 U2K. This one right here is U1 V3J. So I'll put it right under here under the J. U1 V3J. And then this one right here is what? U3V2I. U3V2I. Notice these are like terms. You can combine stuff, right? So here we can combine these, and that'll give us what? Well, that'll give us U2V3. Oh, here you have a common factor of I, so we just factor that out. So let's just write this part first. U2V3 plus U3. Oh, sorry, not plus. I forgot the last step. Now we're going to subtract these two lines from each other. There we go. So we're going to take U2V3 minus U3V2. That's why I've even put them in red. Those are the ones you're subtracting. And we had a common I. And then here you're going to subtract these from each other. So that'll be U3V1 minus U1V3. And you have a common factor of J. So that'll be U3V1 minus U1V3J. And then over here we have U1V2 minus V1U2. But if you notice, that's the cross product. U2V1 minus U2V3 minus U3V2 I. Now you say, oh, that one's wrong. No. Notice you can distribute this. Make that one negative of a negative. That's a plus U3V1. U3V1. And then you distribute the minus, and that's minus U1V3. Oh, so those are still the same. And then this is the same as well. U1V2 minus U2V1. Okay. So this is a mnemonic for helping people remember how the cross product is laid out. You take these diagonals, add them together. You take these diagonals, add them together, and then subtract. If that sounds familiar, that's because that's how you would normally compute a determinant. Huh? Thinking back to just basic algebra, if you had the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and you were going to compute the determinant, you would do exactly this computation here. So one way of thinking about the cross product is it's the determinant of some matrix. In fact, this matrix here, IJK, U1, U2, U3, V1, V2, V3. Okay? So it's you can think of it as a determinant. So go ahead and give this a try. Here are two vectors. One thing to note is that the order does matter. Here we're going to have U first and then V. You say, does it really matter? It turns out yes. The cross product is not commutative. Unlike the dot product, the order of multiplication does matter here, which kind of makes sense. We're almost thinking about these as if they were matrices, right? So, well, with matrices, the order of operations mattered. So here, it at least is a somewhat of a familiar thought that, hey, maybe multiplication is not commutative. We'll talk about a little bit more precisely in the next theorem, but for now, let's look at an example. Consider the vector u to be given by 3, 1, negative 2. And here I've given it in component form, which is the same. It's interchangeable to the unit vector form. And then here's the vector v. Let's say 4, 0, and 1. Okay. So now the question is find the cross product. Find u cross v. And find v cross u. And we can compare. I'll go ahead and do this first one, and then I'll ask you guys to do the second one. All right, let's give this a try. The first one is going to be u cross v. All right, so I'm going to go ahead and use my mnemonic. I could use my definition, but, well, frankly, I never remember this thing. There's a reason why the video started with this already written out rather than the way it usually starts off with me writing it. And that's because if I write it out, there was a small chance I was going to make some error somewhere along the lines. Because I've never, in all the years I've took classes or all the years that I taught, I never remember the order of these. But this always made things a lot easier to remember. If you have a much better working memory than I do, then, well, please go ahead and use that. But I will go ahead and proceed with the mnemonic. I, J, K, and I'll write it again. And then I'll take U, and I'll write that first. 3, 1, minus 2, and then I'll write it again. And then I'll take V, and I'll write that. 4, 0, 1, and then I'll write it again. All right, so here we go. Taking the diagonals from upper left to lower right, that's 1 times 1 times I. Okay, well, that's 1I. 4 times negative 2 times J, well, that's negative 8J. And then 0 times 3 times K, well, that's 0K. All right, so now let's go back the other way. 4 times 1 times K, that's 4K. 1 times 3 times J, that's 3J. And then here, 0 times negative 2 times I, well, that's just going to be 0I. And now once you have those, you're going to subtract. You're going to take these diagonals going upper left to lower right, put those together. You take these going from upper right to lower left, put those together, and then subtract. So that'll give us our result. U cross V, that's 1I minus 0I, well, that's still 1I. Negative 8J minus 3J is negative 11J. And 0K minus 4K, oops, I'm forgetting my notation there, is negative 4K. So here, that's my cross product. Here, since I started off with this in component form, I'll go ahead and end with it in component form. 1, negative 11, and negative 4. If you wrote it this way, that would also be correct. Okay. So go ahead and give this a try. Pause the video and find the cross product of V cross U. It will not be the same as U cross V because the order will be different. Go ahead and give that a try, and once you're done, go ahead and unpause and we'll confirm it together. All right, so here we go. We're going to multiply V cross U. All right, so using the mnemonic, I'm going to say I, J, and K. And then again, I, J, and K. And then I'm going to take, well, since I'm doing V cross U, I need to write V first. Okay, so 4, 0, 1, 4, 0, 1. And then U, 3, 1, minus 2. And then again, 3, 1, minus 2. Going forward, that's going to be 0I. That's going to be 3J. And that one's going to be 4 times 1, that's 4K. Now, going backwards, that's going to be 1I. That's going to be negative 8J. And that one will be 0K. And you're going to subtract those lines from each other. Note that when you subtract them, it's not totally different from what we had above. It's the opposite. 0 minus 1I, that's negative 1I. 3 minus a minus, in other words, 3 plus 8, that's going to give us 11J. And then 4 minus nothing, that'll give us 4K. So it's not totally different. In fact, it's the exact opposite of the original. Minus 1, positive 11, and positive 4. This is not a coincidence. The cross product is not commutative, but if you switch the order, all that changes is the signs. Right? One is the opposite of the other. We'll see that stated explicitly in this coming theorem. So let's take a few vectors and a scalar and see how they interact. Theorem. Let's go ahead and have a few vectors. Let's say the typical u, v, and w. Let u, v, w be vectors in space. Again, the cross product will not be defined in the plane. Be vectors in space. And let C be a scalar. Just a regular number. All right. Then the following things are true. The first one you just saw an example of. The cross product is not commutative, but it almost is. If you change the order of the elements being multiplied together, it's simply the opposite of the original. So u cross v is the negative of v cross u. The second thing is that just like the dot product, the cross product also exhibits the distributive property. So u times this sum, that u would simply distribute. It still stays the same kind of multiplication. So this is going to be u cross v plus u cross w. So thankfully, you don't have to remember something different for the different multiplications. Scalar multiplication distributes, the dot product distributes, and now the cross product distributes. The third thing here, we see the cross product multiplied by a scalar. It turns out that, well, just like with the dot product, this is associative. You can either cross product first and then multiply by the scalar, or you can you can say u multiplied by the scalar first and then cross multiply times v. Or you can even move that over here and say that's going to be u cross multiplied with cv. Just like that. When we look at the dot product, we see that if you take the vector u and dot it with the 0 vector, it gives you a number 0, because dot products gives you numbers. Well, here if you take the vector and cross it with the vector 0, you get the 0 vector. All right? Compare that to the dot product. Here, let's put this off to the side. Recall from a previous section, u dot 0 is equal to the 0 number. Dot products give you scalars. Cross products give you vectors. This one's a little unexpected, and it has to do with the geometric properties of the cross product, which we'll explore here at the end of the section. U cross U is a little unexpected. U cross U is 0, the 0 vector, mind you. We'll talk about that one here in a moment. And then finally, the last product is that if you take a dot product of a cross product, then it doesn't matter how you associate those. If you have u, v, and w, if you want the cross product of these and then the dot product, you know what? You could actually just switch the multiplications. You could say, let's take the cross product of this one and then dot that one. So if you have one of each multiplication, it doesn't matter which way you do it. You can multiply those as a dot and those as a cross, or you multiply those as a cross and then over here as a dot. Now, the order of operations is a little more explicit here. We're going to put parentheses here. You have to do the cross product first. If you have a dot product and a cross product, it doesn't matter which way you orient it, but you always have to do the cross product first. Why would that be? Pause the video for a moment and think about it. Why would you always have to do the cross product first? Why is it not possible to do the dot product? Pause the video, and when you have an answer, go ahead and unpause it. Whenever you take a dot product, you get a scalar. Dot products are numbers. But if you do the dot product first, this would be a number, and this would be a vector. Vector cross a number. That's not defined. The cross product is only defined between a vector and another vector. So if you do the dot product first, you're saying vector cross a scalar, which is undefined. Okay? So you always have to do the cross product first. Okay, so the proofs of these are all by definition. Here, let's start with number 1. The proof of number 1 is fairly straightforward. Okay, what is U cross V? Well, let's see. I have a definition of that. So, U cross V, by definition, is U2V3 minus U3V2I minus U1V3 minus U3V1J plus U1V2 minus U2V1K. Like that. Okay, well then what's V cross U? Okay, well V cross U would be well, the other way around, wouldn't it? Over here, wherever I see a U, I would replace it with a component of V, and then all the components of V would be replaced by components of U. Okay, so this would be, instead of U2V3, it would be V2U3 minus V3U2. I minus, and again, instead of U1V3, this would be V1U3, V1U3 minus V3U1. It's always the first component of the one on the left, and then the second component of the one on the left, and the third component of the one on the right. By switching them, well, now this is the one on the left, so it goes first. And this is the one on the right, it goes second. And we do that all the way down. Plus V1U2 minus V2U1K. Oh, but notice that's what these are. Oh, except all the signs are wrong, right? That's U2V3. That's U2V3. That's U3V2. That's U3V2. This is the same as that, and this is the same as that. Oh, but the signs are wrong. Oh, okay, so what happens if I multiply all of this by a negative? Like this, a negative scalar. Oh, well, then it just changes all my signs. So now this one's positive. So that'll be positive V3U2. And now that's a negative, so minus V2U3I. Minus, and now then we're going to switch these. So that'll be a positive now. So that'll be positive V3U1. And now that's a negative, minus V1U3J. Plus, and again, that'll make this a negative and this a positive. So that'll be positive V2U1 minus V1U2K. But if you notice, that's exactly what the first one is, right? U2V3, U2V3 minus V3U2, U3V2 minus U3V2I, and so forth and so on. So that means that U cross V equals negative V cross U. All of these properties are proved exactly the same way. You go by definition. You say, okay, what's the definition of this? What's the definition of this? And then compare them. Right? All of these are proved the same way. So proof of number 1 is here. The proof of 2 through 6 is omitted due to, let's say tedium. It's omitted due to tedium. It's a very tedious process. You basically just have to write the definitions and compare. So here we're not really going to gain any more insight into these by proving them beyond what we already see here. It's enough to know for now how they would be proven. How would you prove it? You'd write out the left side in component form, you'd write out the right side in component form, and then compare. So there we go. proofs of 2 through 6 are omitted due to tedium. All right. Now, I did mention something about this one, though. I said something about this was unexpected. Now, if you actually just do the multiplication, u2, u3 minus u3, u2. Oh, that's 0. u1, u3 minus u3, u1. If both of these are u's, this and this are exactly the same. So that's 0, and that's 0. So from a definition standpoint, it's really straightforward to prove. Just all of these there are no v's. They're all u. u2, u3 minus u3, u2. Oh, that's 0, and that's all the way down. So we don't really gain any insight in terms of a proof here. There's more insight to be gained from considering a geometric interpretation of this. So that's going to be our next theorem. And in this one, we actually are going to prove things just a little bit more because it's not quite so, well, tedious. Theorem. All right, let's see here. We're going to begin with a couple of vectors in space. Let u and v be non-zero vectors in space. Okay. And since we're talking geometric, since we're talking about geometric interpretations, we should probably have something that's well, geometric in nature. Let's give an angle. Let theta be the angle between the two vectors. Whenever you have a vector, you can denote lots of angles between them. As always, we mean the shortest angle between them. Okay. All right. So the following properties are true in these circumstances. If you take the cross product of u and v, this is orthogonal to both of the original vectors. What does that mean? Well, geometrically, what it means is give me two vectors. Here's one, and here's another one. Okay. Call this one the vector v, and I'll call this one the vector u. Okay. Find their cross product. Their cross product will be sticking straight up, just like this. The cross product is perpendicular. Well, okay, orthogonal, to use the proper term, is orthogonal to either of those vectors. This is going to become very useful later on because where are these two vectors? They're on the plane. Which plane? Well, the plane I just drew them on. Okay, so what do I find when I take their cross product? I find a vector in another direction. Oh, that means we can define something external to the plane. That'll become useful in a few sections. But for now, geometrically, if you have the cross product of two vectors, it's another vector that is perpendicular to either of these. It'll form a 90-degree angle with u. It'll form a 90-degree angle with v. The second thing of this property is that if you take that cross product and you find its magnitude, it's equal to the magnitude of u times the magnitude of v times the sine of the angle theta between the vectors. This should remind you a lot of a similar property for the dot product. You will recall an alternate definition for the dot product. Recall the alternate definition for the cross product being, the dot product is u dot v is equal to the product of the magnitudes of u and v times the cosine of theta. If you change that cosine to the sine of theta, well, now instead of having a dot product, we have a cross product here. Notice this is a scalar. So here, this couldn't be the cross product because the cross product is a vector. A vector cannot equal a scalar. Oh, the magnitude of that is that scalar. So that should remind you very closely of a product we had for the dot product. Okay. Third property, u cross v is equal to the 0 vector if and only if u and v are parallel. Oh, well, u and v are parallel. Well, you know what's parallel to u? U is parallel to u. Everything's parallel to itself, right? Okay. Hey, look, these two are parallel because they're going in the same direction. Hey, that one's parallel to itself because it's going in the same direction as itself. Yeah, it's a vacuously true statement, but hey, welcome to math. Sometimes vacuously true statements are still considered. Here, u cross v is going to equal to 0 if and only if u and v are parallel. Well, u is parallel to itself, so that means u cross u would be 0. Hey, there we go. That's another way of thinking about this one. U cross u is equal to 0. More generally and geometrically, that's a way of thinking of, that's a way of saying, hey, if you take the cross product of any two things that are parallel, the result is a 0 vector. And the last one is very geometric in nature. Let's say you take the cross product of u with v, and you take the magnitude. This is equal to the area of a parallelogram. Oops, I don't know how to spell parallelogram. Parallelogram? Parallelogram. There we go. Parallelogram with u and v as its adjacent sides. So here we can draw that as, okay, here's the vector u, and here's the vector v. Okay, imagine completing the drawing of a parallelogram there. Okay, well, I could draw a line that's parallel to this one. That's the same length. And I could draw a line parallel to this one. That's the same length. Okay, the area of this parallelogram is the magnitude of the cross product. So find me the cross product. That's a line that sticks straight out. Right? It's a line that sticks straight out, perpendicular to either of those. How long is that? How long is this? Oh, it's 16 units long. Okay, well then this area is 16 square units. All right, so now let's talk about the proofs of some of these. Question number 2, I believe, is proven in your textbook. So this one's within the actual context of the section. They walk you through it step by step. So we're not going to worry about this one because, well, why would I read to you something that you can read yourself, right? This top one and this third one are left as exercises. They're nicely accessible to us if we just take a few moments and go back from definition. So I haven't decided yet which one I'll assign you, maybe both, but well, you'll see that in the assignment section, yeah? And then, so let's go with number 4. Right? I don't want to do number 1 and number 3 because I'm going to assign at least one of those to you guys. And number 2 is already done for you. So let's talk about number 4. All right, so here's a parallelogram. In fact, it's got a base of V and a diagonal here. This side is U. Okay, well, thinking back to geometry, the way we find the area of a parallelogram is you multiply. So area is equal to base times height. All right, well, I know the base. The base is this vector V. Oh, yeah, but this is supposed to be a number, right? It's supposed to be like 12 inches or something like that. Oh, okay, well, then I need the magnitude of the vector V. Okay, so that's the magnitude of the vector V times the height. You say, well, that's the vector U, right? Well, no. Height is straight up and down. So that's this right here. Oh, well, how do I find that? Oh, well, height is perpendicular to the base. That's going to be a 90-degree angle. So that means that this right here is a 90-degree triangle, we can have an angle here, which we'll call theta. Hey, look, that was even part of the theorem, right? We have an angle between the vectors u and v. Okay, well, how do I find this height? Well, let's see. I know the vector u, and I'm trying to find this height. And I know this angle. Okay, so I have an angle, the side opposite, and the hypotenuse. Oh, that's the sine of the angle theta. Right here. So this height is equal to, well, not equal to, it has a magnitude that is, well, let's see here. Sine of theta is this divided by the magnitude of u. Okay, so if I just take the magnitude of u and multiply it over to the other side, that's going to give me the magnitude of u times the sine of theta. Right? Sine of theta is equal to this length divided by the magnitude of u, opposite over adjacent. So if I take the adjacent and multiply it over to the other side, sine of theta times the hypotenuse is the length of the adjacent side, of the opposite side. Okay, so that has to be length magnitude of u times the sine of theta. Okay, so that's my height, magnitude of u times the sine of theta. Oh, but that's number 2 that's proven for you in your book. The magnitude of u times the magnitude of v times the sine of theta is equal to the magnitude of the cross product. And we have our result. Why did I do the proof in the corner? I have no idea. Proof. Of number 4, I should say, right? All right, so there we go. All right, so even though we talk about the proof of number 4 here, let's talk about an example of number 1. Because this one, as I mentioned earlier, is going to be a very useful property to have. We're going to use this to define lots of things later on, as we'll see, and in fact, really pretty soon in the next few sections. So let's just give an example of this. I hope if I was organized, right? All right. So let's go ahead and find a vector that is orthogonal to both the vector u, which we'll give as -5, 2, 2, and the vector v, which we'll give as 0, 1, 8. Okay. Go ahead and give that a try. Basically, you're just computing a cross product. So go ahead and pause the video, give that a try, and once you're done, go ahead and unpause and we'll go through it together. All right, so all we're doing is finding the cross product. U cross v. Incidentally, you could do v cross u. You might say, well, wait a minute, how would that work? I mean, you have u cross v and v cross u are not the same. So you're saying there's more than one vector that's orthogonal to both of those? Well, sure, there's 2 of them. Let's say I have this vector and this vector here. All right, what vector is orthogonal to that one? Well, this one that sticks out of the page. Okay, well, there's only one vector that sticks out of the page. Well, that's true, but there's also the vector that sticks into the page, going back the other way. So starting from here, back into the page. So you could have this vector coming out toward us, or you could have this vector going away from us. And both of those would be at a 90-degree angle to either of those. That's a little hard to draw. We can think of it more of as a solid. You have this plane right here, and I have 2 vectors on this plane. Then I could have something that sticks out of this pad, or I can have something that sticks back out of this pad in the opposite direction. And both of those would be orthogonal to the vectors on this pad. All right. So here, you can either do u cross v or v cross u, and they'll both give you a vector that's orthogonal to both. So let's go ahead and compute that. I, j, k, I, j, k. -5, 2, 2, -5, 2, 2, 0, 1, 8, 0, 1, 8. All right, so that'll be what? 16i plus 0j plus a negative 5k, so I'll just say minus 5k. And then I'm going to subtract away. That's going to be 2i. That one will be negative 40j. And that one will be, looks like 0k. So that'll be 16 minus 2. That's going to be 14i. 0 minus a negative 40. That'll be plus 40j. And negative 5 minus 0, well, that's still negative 5. Okay. So the cross product of these two, u cross v, is equal to 14, 40, negative 5. Note that this is orthogonal to both. By definition, two things are orthogonal if their dot product is 0. So let's check that. If I take u dot u cross v, let's see what that is. All right, well, that's going to be negative 5, comma 2, comma 2, dot with 14, comma 40, comma negative 5. Let's see here. Negative 5 times 14 is negative 70. 2 times 40 is 80. And then 2 times negative 5 is negative 10, which sure enough is 0. So u is orthogonal to u cross v. Likewise, with v, that would be 0, 1, 8, dotted with 14, 40, negative 5. 0 times 14 is 0. 1 times 40 is 40. And 8 times negative 5 is negative 40. And sure enough, that's 0 as well. So the dot product of u with the cross product is 0. The dot product of v with the cross product is 0. And therefore, that means that the cross product is orthogonal to both u and v. Incidentally, as a follow-up example, here we found the cross product of these two vectors. Gives us this. A follow-up question. Let's go ahead and find the area of the parallelogram with u equal to negative 5 to 2 and the vector v equal to 0, 1, 8. So I'm using the same two vectors as before. We already know the cross product right there. Find the area of the parallelogram with those two vectors as adjacent sides. You might want to try that one. Go ahead and pause the video, and once you're done, go ahead and unpause. We can go through it together. All right. The area of the parallelogram is going to equal to the magnitude of the cross product of the two adjacent vectors. Like that. Which is the magnitude of, well, we already computed that. That was 14, 40, and negative 5. So now we just need to go through and find that magnitude. Remember, to find the magnitude of a vector, that's basically just the distance formula. That's going to be the square root of the sum of the squares of the components. 14, 40, negative 5. So that'll be the square root of, oh, let's see here, 14 squared. That'll give us 196 plus 40 squared. That'll give us 1600. And then negative 5 squared, that'll be positive 25. So that'll be the square root, let's see, 17, 18, 21. And that's our result. So that must mean that our area, the area of the parallelogram, is the square root of 1821 square units. This may also seem to be just a trivial little fact. However, this will also become very important to us later. The two most important things that we're going to build from to much more advanced things in this course are going to be these two facts. The fact that you can find the area of a parallelogram using the cross product of the two vectors that define its sides, and the fact that you can find a vector that's orthogonal to two other vectors using the cross product. Those two things will develop a lot in the coming sections and the coming chapters. But for now, we have one last theorem. In this theorem, we're going to define the triple scalar product and one of its results. All right? So let's see here. We're going to start off with three vectors. We'll say u, v, and w. Let u, v, and w be, let's let these be non-zero vectors. Then we're going to define, well, you know what, let's go ahead and write out the computation and then we'll state the definition at the end. So let these three be non-zero vectors. Then the volume of the, oh, let's see if I can pronounce this correctly. Parallelepiped. Parallelepiped. It's a box that got squashed in the mail. A parallelepiped is it's almost like a box, except that the sides don't have to be perfectly at 90-degree angles as long as the opposite sides are parallel to each other. So basically, here's a parallelogram on the plane. Now imagine making a box out of that. So something like something like that. It's a box that got squished a little in the mail. Right? Okay, so the volume of the parallelepiped with vectors u, v, and w as adjacent sides so here let's say that's your u, that's your v, and that's your w. So three vectors all starting from the same point. Those define your adjacent sides. Okay? If you take the volume of that, that's going to equal to the absolute value of u dotted with v cross w. Here we say absolute value just because, well, we can't have a negative volume. So here's the absolute value of u dot with the cross product of v and w. This right here, we've actually seen this before. It's in part of a previous theorem here. U dot v cross u. In this theorem, we said that we could multiply the cross and then the dot, or the dot and the cross, like that, as long as the cross product is always done before the dotting. Right? So we've seen this right here. This and this, regardless of whichever one you do, this is called the triple scalar product. Triple, obviously, you have three vectors. Scalar product, because here you're going to end up with a scalar. You take the cross product, that's a vector, and then a vector dot a vector is a scalar. So this is called the triple scalar product. So over here, the volume of this box is going to equal to the absolute value of the triple scalar product. The proof of this one is really very short. The volume of a parallelepiped, a box, it's base times height. Okay, well, what's the base? Well, right here, the base is just the parallelogram down here on the ground, for lack of a better word. Okay. All right, well, I know the area of a parallelogram. In a previous theorem, we saw that's just the cross product of those two vectors, w and v. Okay, so my base is going to be the cross product of w with v. Oh, but the cross product would give me a vector. I want the area. Okay, then I need the magnitude. That's from our previous theorem. If we take the magnitude of the cross product, that's the area of the parallelogram, which is what this is. It's a parallelogram. Okay, so now we got to find the height. Well, remember, the height is always straight up and down. It's going to be perpendicular to the base. So from here, we will drop a line straight down to find our height. Okay, well, our height is simply, well, I got to figure out how far up this u takes me. I know v and w are down here on the ground. U is the only one that's taking me up. Okay, well, the length of u is too much because this is slanted. I just got to figure out how much of u is going in that direction. Oh, that's the projection. If you take u and project it onto this line right here, well, okay, but which line? Well, I want this line right here, the one going straight up and down. Well, yeah, but how do I find that line? Oh, that's another part of our theorem. If we want to find something that's orthogonal to two vectors, I find the cross product. Hey, look, we just said the height is going to be orthogonal to the base, and the base is made up of those two vectors. So what I need is I need the projection of this u onto this orthogonal vector. I find the orthogonal vector by taking the cross product of w with v. So the height is going to be the projection of the vector u onto this line that's perpendicular to my base, or in other words, perpendicular to these two vectors that make up my base. Oh, okay, it's going to be the line that's the cross product of v with u. V with w, like that. Okay, but by definition, we know the cross product. The cross product is going to be given by, actually, my bad. This projection would give me a vector. I want a number, right? Base times height. So here I want the magnitude of the projection. There we go, much better. Okay, so I want the magnitude of my projection. So that's going to be the magnitude of the projection. Okay, we know the definition of the projection. U projected onto this, that's going to be u dot this. U dot this thing. Divided by this thing times itself. Squared like that, times the actual vector that you're projecting onto, which again is just w cross v. Okay? Now notice, this should be a vector. Okay, but this should be a vector. Okay, but we're looking for the magnitude of the vector. Okay, so when you take the magnitude of that vector, notice that's already down here. Magnitude. Oh, basically this divides one of these. So here we can write this as the magnitude of w cross v. I've just left that alone. Over here, I'm going to write this as, okay, the magnitude of this times that is really just the magnitude of this times the magnitude of that. So that'll be u dot v cross w over the magnitude of w cross v squared times the magnitude of w cross v. Right? That's my base, and this is my height, or rather the magnitude of my height. But notice that and that perfectly cancel this one. Two of those cancel with two of those. And so we're left with the magnitude of the triple scalar product. Oh, but that's not a vector, is it? That's just a number. That's a vector dotted with another vector, that's a number. Oh, so you're taking the magnitude of a number. Oh, well, the magnitude of a number, that's just called the absolute value of the number. It's how big the number is. So it's going to be the absolute value of u dot v cross w. In other words, it's the absolute value of the triple scalar product. And that's our result. All right, so that is it for our section for now. At this point, it's just another geometric property. However, this is also laying the groundwork for something coming on later. But this will not, we won't see this much in this chapter. However, keep this one in mind. We will revisit this one in a few chapters when we start talking about volume under surfaces. Because after all, hey, that found a volume for me. You say, well, how is that related to general things? Calculus is a subset of analysis. Analysis is a field of math. Calculus just happens to be one little part of analysis. The thing about analysis is it's very, very predictable. We don't have a lot of tools. We pretty much do the same thing every time. Now, we get very good at doing that one thing, but ultimately, analysts basically do one thing, and that's you give us a problem. We don't know how to solve it, okay? But we can give you a guess. Now, it's not a terrible guess. In fact, it's probably a pretty good guess. But it's not a perfect guess. So it's not really the answer. Oh, but is there a way to make that guess any better? Sure, you can make the guess better by doing this. Okay, so do that an infinite number of times and you get the perfect answer. You've seen that already. In Cal 1, you want to find the slope of a tangent line. I don't know how to do that. Okay, I find the slope of a secant line. All right, is that okay? I mean, it's not bad, but it's definitely not the right answer. Can I make this any better? Well, I guess I can make it better by taking this and moving it a little closer, and that gives me a better approximation. Okay, well then keep moving it closer forever. Take the limit as this distance goes to 0. You see it again at the end of Cal 1, beginning of Cal 2, when we talk about area. Find the area under that curve. I don't know how to do that. Okay, well, give it your best guess. Okay, well, my best guess is the area underneath that rectangle. Well, that's not a very good guess. It's not bad, but it's clearly not right. Can you make it better? Yes, I can make it better by cutting it into 2 rectangles. Now that's a better guess. Okay, so keep doing that. Cut it up not into 2 rectangles, not into 20, not into 2 million, but keep going forever. Here, don't bring it an inch closer. Don't bring it half as close, or a quarter of the distance, or an eighth the distance. Keep going forever. Same thing here. Keep dividing this up forever. That's the integral. In this course, we're going to take this and just expand upon it. The same idea. Hey, here's an object in space, like a dome, a bubble or something. Hey, find the volume of that object right there. I don't know how to do that. Okay, well, what's your best guess? Well, I know how to find the volume of a box, base times height. Okay. Can you make that any better? I guess I can use like 2 or 3 boxes. Yeah, that is better. Okay, now do that forever. Analysts, we really only have one trick up our sleeves. You give us a question we don't understand, we're going to give you a guess. And then we're going to say, okay, our guess is not perfect, but we can make our guess better by doing this, usually by increasing the number of things that we're using to cut things up into. Okay, so now we just do that thing forever, and there's the perfect answer. You're going to see that repeated over and over again throughout this course. A lot of the development of the proofs that we will have in this course will mirror very closely what you see in Cal 1 and Cal 2, now in space and beyond. Beyond? Of course, there's nothing that limits us to 3 dimensions. We can keep going beyond that, which we'll see a little of in this course as well. So that's a little bit of a preview of what's coming forth, and I do hope that you take away from that these theorems are not trivial. They're not just, oh look, here's a cute picture, or in my case, not such a cute picture, but here's a picture, and you can connect this cross product or this dot product or this triple scalar product to some physical phenomenon, to some physical interpretation. It turns out that that's not just a cute little example of a volume or an area, but it'll be vital to our work in analysis, to our work in generalizing the concepts of Cal 1 and Cal 2 into space and higher dimensions. So that's all the time we have for today. If anybody has any questions, comments, or problems, please reach out, make a note of those, and let me know. And I hope everyone has a nice day.